We saw what are the generic expectations in terms of observing galaxy formation, but now let's look at the observations themselves. How would we go about it? First, recall that most of the energy from young forming galaxies, say protoellipticals, would come from conversion of hydrogen into helium in stars, adding up to about 10 to the 60th ergs overall. And the question is then, what is the time interval over which this energy is released? Because what's observed is not energy, but luminosity. So if we confine ourselves to the lifetimes of typical starbursts, which are some tens of millions of years, or maybe free fall timescale of the order of 10 to the 8 years, or maybe merger timescale of the order of 10 to the 9 years, we get roughly a range of luminosities that are between 10 to the 11, 10 to the 12 solar luminosities. And at the redshifts of interest, that maps to apparent magnitudes of the order of, say, 25 to 30, give or take, depending on exact redshift and the luminosity of the actual protogalaxy. Few percent of that energy will emerge in form of emission lines, most notably Lyman alpha, if it's unobscured. And that would form a good way of finding galaxies. However, the big question is this luminosity obscured by dust, in which case we have to look in a submillimeter, or just naked stellar photospheres, in which case it emerges in restream UV and will be observable in visible light or near-infrared light today. Since at first there is no dust, at the very first stages, we must be looking at unobscured galaxies. Emission lines would then form a very good indicator of star formation at high redshifts, and there are several ways in which we can do this. The simplest one is putting a dispersing element, like prism or grism, in front of the telescope optics, and so every source gets dispersed into its spectrum. That's called a slitless spectroscopy. This works for relatively bright objects, from the ground at least, because at any given pixel for a given spectrum you only get light from that wavelength, but you get light from all wavelengths from the background or foreground. So for really faint objects this will not work from the ground, although it's been done from space using Hubble Space Telescope. An alternative is to use standard long slit spectrograph, in which case a dispersed image of a narrow but long slit is being detected, and that will work fine over a very small area in the sky, but over a large area in redshift. And because the light is being dispersed properly, you can do sky subtraction, the depth is pretty good. Finally, you can take narrowband images, which bandpass is very small. It will select emission lines at particular redshift, so it can go fairly deep over reasonable area in the sky, as much as the detector covers, but only over a tiny redshift range. All of these have been used, and all of them have produced some results. The narrowband imaging has been very effective, especially for looking for Lyman alpha line of neutral hydrogen, the strongest unobscured recombination line. This is an example of the first high redshift galaxy found using that technique. It is a quasar companion, redshift 3.2, and you can see on the bottom right image what it looks like in the light of Lyman alpha line alone. The quasar in the middle and its companion galaxy off to the side are very clearly seen. Yet on the continuum image just above it, the companion galaxy is just as faint as many others. So this is a good way to select emission line galaxies at high redshift, and it's been very productive so far. Another possibility is to just look on a long slit, taking spectra of perhaps other objects. In this case, here is a spectrum of quasar, that's the black streak in the top left, dispersed over some range of wavelength, and away from it, you see an emission line that's detached. This is a background galaxy redshift 6.4 or so, which is unrelated to that quasar. So it's pure chance that one finds objects like this. However, there are so many galaxies in the sky that this is not so crazy, and in fact, a number of galaxies have been found using this technique. This is maybe not very efficient, but it's completely unbiased, except, of course, for the line flux itself. Here is an example of one of the most distant, if not the most distant galaxies selected using narrowband imaging which are also confirmed using slit spectroscopy. This is the redshift of 7. The 3 images show 2 continuum images. The galaxy light is diluted completely, and a narrowband image in which it stands out because of its strong Lyman alpha emission. The plot at the bottom shows the spectrum that confirms that that's indeed what we're looking at. A very popular technique that goes deeper than spectroscopy is the Lyman break imaging. We talked about that in the context of galaxy evolution. Remember, this works as follows. There is a strong continuum break at Lyman alpha, or maybe Lyman limit, due to the intergalactic hydrogen or gas in galaxies themselves. And so if you have one filter blueward of that break and at least 2 others redward, you can look for objects that look blue or flat spectrum in the red, and then suddenly very red, that is with a strong drop in the blue end. This is illustrated on bottom with actual image from Hubble Space Telescope. Now you can see that galaxy is well detected in 3 filters redward of the Lyman break, but is completely absent from the one that's bluer of the Lyman break. This is a very effective way of finding high redshift objects. However, one has to trust that this is indeed the correct break, and usually one would like to get confirming spectra to make sure. Here is an example of an object, or actually 2 objects, seen in Hubble Ultra Deep Field where this technique has been applied. There are 3 detections, the Hubble black points, and everything else is upper limits. What's drawn through this are a couple model spectra of evolving stellar populations, and it's probably obvious that more than one kind of spectrum can be used to fit these things. The authors go through certain arguments why should be in particular the one that corresponds to high redshift Lyman break, although obviously there is some uncertainty involved. If you believe that it's the high redshift object with a break that's been detected here, then you can estimate photometric redshift, and that's what's given here. At this time, all of the galaxies beyond redshift of 7 or so have been detected using this technique. There are no spectroscopic confirmations so far because they're just too faint. We have to wait for the next generation of telescopes, say 30-meter telescope. And almost surely some of these really are at high redshifts, but it's possible, given the ambiguity of fitting models, that some of those really are at lower redshift, maybe highly reddened galaxies, and so these have to be taken with a grain of salt. Here is a selection of such high redshift galaxy candidates from Hubble Ultra Deep Field, and you can judge by yourself just how reliable these detections really are. Their estimated photometric redshifts are shown on the right, and indeed they seem to always make an appearance in some red band but then disappear on blue side. On the other hand, there is, in addition to measurements of faint signals, there is a question of interpretation of fitting the correct stellar evolution model. Now, assuming that this is actually correct, one can extend the Maddow plot, the history of star formation, and now we see that finally, past about redshift 4 or 5, the star formation density declines at high redshifts, which is what you expect. You begin with no galaxies whatsoever, you build them up. As we already know, there is a fairly broad maximum or plateau of star formation history down to redshift 1 or 2, and then decline towards the present day. So this makes sense, and almost surely some of this is right, although there may be some contaminants in these ostensible high redshift galaxy candidates. Another interesting thing happened, that some of these ostensible high redshift objects, when observed in mid-infrared, show some signal, which would correspond to somewhat older stellar population, maybe up to 1 billion years old, meaning that they have to start very early on at very high redshifts in order to actually have this evolved stellar component added to the brand new young stars that we normally look for. And finally, how do we connect formation of galaxies with that of large-scale structure? You remember the idea behind biasing, that the first objects that form at the highest peaks of the density field. And so you expect that first galaxies will be strongly clustered in what will be cores of future clusters of galaxies. This is indeed seen. We've seen companions of galaxies around quasars as well as in the field, and here is a set of Lyman alpha emission line galaxies around redshift of 5, where it's been seen that they cluster fairly strongly. Also, the most distant quasars known, past redshift of 6 or so, seem to show excess number of galaxies around them. Not always, and this is a very difficult observation, but at least in some cases. And that fits very well with the idea of biased galaxy formation. Next, we will turn to the reionization era, the frontier of modern observational cosmology.